Good morning, everybody. I'm going to help you out with number 10 on the acid and base summative review guide. So it's a 4-part question, A, B, C, and D. Looking at a little bit of buffers, a little bit of titrations. So just trying to kind of sort it all out, and I'll help you out in this video. All right, here is that dreaded number 10. On the surface, it might look like a typical problem. I mean, it is. But the reality is it's kind of like 4 big separate problems. So we're going to go through each one, help you out. Truthfully, on an FRQ, I would probably give you maybe one of these within an FRQ, not all 4 of them at once. That would be a little too time consuming. Okay, so we have a buffer. It's already a buffer because it contains a certain concentration of a weak acid and a certain concentration of a salt, and that salt happens to have the conjugate base of the weak acid. The pKa of the acid is provided. So letter A just wants us to find the pH of the buffer that already exists. So remember, a buffer is a weak acid and its conjugate base. So if I were to see an ice table, I'm going to have a starting amount here. I'm going to start with 0 molar of this, and I'm going to have a starting number here. So we have to have both of those initially for it to be considered a buffer, a weak acid and its conjugate base, or a weak base and its conjugate acid. So to solve this, I know, well, first of all, Ka equals, I always write the Ka expression as soon as I write the acid breaking apart. So I could do an ice table. I know the pKa, so that allows me to find Ka. I can do an ice table with a common ion, a starting amount here and a starting amount here to find the pH. Or I can do the Henderson-Hasselbalch, which is kind of a shorter equation to help you solve for the pH of a buffer system when you have a weak acid and its conjugate. We always do the base over the acid, remember, in that Henderson-Hasselbalch equation. Couple of thoughts. Why did I not do a BCA table? Why did I jump right into ice or right into Henderson-Hasselbalch, one or the other? Well, because this is just a buffer sitting there. I'm not adding anything to the buffer. So when you have an acid and a base mixing, you're automatically going to have a stoichiometry BCA table because acid and base are going to react until one runs out. But in this case, I have the buffer just sitting there, a weak acid and its conjugate. Well, we know a weak acid is going to be at equilibrium, and in this case, it's trying to establish that equilibrium with a common ion already present. So here it is kind of worked out. I put in the starting concentrations that were provided in the problem. I set up my Ka expression. I know the pKa, so 10 to the negative pKa will give me the Ka value. And so then when I set up my ice table, we move towards the zeros, even though there's a number here, there's 1 0. So minus x, and then these are plus x, and I can fill in my equilibrium line. Well, I know Ka, and so then what I can do is I can plug in my equilibrium, omit my x's. It's to the -4th, so I'm running a risk here. Normally the -5th times 10 to the -5th is safe for the 5% rule. But when I checked my answer, I was less than 5%. So we are good there. Again, times 10 to the -4th is kind of that gray area. Sometimes it's a quadratic, sometimes it's not. Anyways, when I solve for x, I get the concentration of H plus at that equilibrium. And we know the pH is equal to the negative log of H plus at equilibrium, so I can find the pH. Or we can do the Henderson-Hasselbalch equation. So the pH is equal to the pKa plus the log of the base, the conjugate base, over the acid. And all I'm doing is plugging in the molarities that were given in the problem, and I can find the pH. So this is a buffer, and in this case, we have a little bit more of the conjugate base compared to the weak acid. But at the equilibrium point, here you can see as well more base over the acid. All right, for letter B, we have our buffer, but now what I'm going to do is I'm going to add 10 mils of 0.2 molar HCl. So if I'm adding HCl, remember, that's a strong acid, so whatever the concentration of HCl, that's going to be the same concentration as H+. So the hard part about a buffer problem when you add an acid or a base is you need to figure out who the H plus is going to react with, because right now I have a weak acid and a conjugate base, and I'm adding some H plus. So this H plus is going to react until one thing runs out with either the weak acid or the base. Well, think about it. H plus, does it want to react with something that's neutral or something that's negative? Well, positive likes a negative, and think about it. H plus is acidic. We want to react with the conjugate base, and that's right here. So I can do that reaction, H plus that we're adding, plus the NO2 minus, those are going to react to form HNO2. I need to do a BCA table and a one-way arrow because this acid is going to react until one of these two things runs out. The trick, though, is I'm going to have a starting number of moles of everything. So we have the moles here that we added, we have the moles here from the original buffer, and we also start with moles here from the original buffer. But either way, it's a one-way arrow. The reaction is going to happen. Acid and base will react. So this is going to be used up. Some of it will be used up, and we're going to make some of this. So basically, we're just adding to the original amount of that weak acid. So let's check it out on the next slide. All right, so the first thing we need to do in order to fill out this BCA table is actually get the starting amount of moles of everything. So for HNO2, we have 100 mils and it's 0.2 molar. So that's 0.1 liters. Remember, molarity is moles per liter. So I just crisscross multiply. So multiply 0.1 times 0.2. I get 0.020 moles of HNO2 to start. So that's what I'm putting right here. For the NO2 minus, remember KNO2, the K is a spectator ion. It comes from the strong base KOH. So the K plus does not have any acidic or basic properties, but NO2 minus is my conjugate base. So we'll take the 0.0300 liters and times that by 0.25, crisscross multiply, gives me the moles of NO2 minus to start. And then we're adding from letter B, we're adding to it 10 mils of 0.2 molar. So that's 0.01 liters and then times 0.2. So that gives me the starting moles of the H plus. So I put that in my beginning. I'm going to use up X, and how do I figure out what X is? Well, I'm going to take the starting amount of H plus, divide it by 1, take the starting amount of this, divide it by the coefficient 1, and the smaller one is X. So in this case, the 2.0 times 10 to the negative third is my X. So I'm going to just take 2.0 minus that X, gives me 0. 0.0075 minus that X gives me how much is excess, and 0.02 plus that X gives me the total amount of HNO2. So now that we've done the stoichiometry, the reaction happens, and I have these values sitting there, right? So the stoichiometry, the reaction happens, but now I see that I have leftovers of the conjugate base and the weak acid. So hopefully your brain is saying ice or Henderson-Hasselbalch, because we have an equilibrium now that can occur once this stoich happens, once this reaction happens. Now I can establish equilibrium with the weak acid and its conjugate base. Let's check it out on the next slide. All right, so I take the moles from the end of the BCA table, and we want molarity for ice or for Henderson-Hasselbalch. So I'm going to divide those by the total volume. So I added up the two solutions from the buffer and the acid that we added to get a concentration of each, the conjugate base and the weak acid. And now it's your choice. You can either do an ice table with a common ion, so these molarities become our starting values. And we know the Ka of HNO2, so we can solve for X, omit, do the 5% rule, and solve for X, which would be H plus at equilibrium, and then take the negative log of X, which is the negative log of H plus at equilibrium to get our pH, or we can take those concentrations and plug it into the Henderson-Hasselbalch. They gave us the pKa from earlier in the problem or at the very beginning, and then we're just going to take the concentration of the conjugate base over the weak acid. And look, they match. That's a good sign. All right, the next problem. How many milliliters of 0.1 molar NaOH would be needed to neutralize? So I see that word neutralize, and that tells me that we're probably talking about stoich, where the moles of the base equals the moles of the acid, stoichiometrically, or think about the equivalence point. And then what would the pH be at this point? Well, if we're talking about neutralization, I'm asking for the pH at the equivalence point for this essentially titration. Okay, so let's kind of think frame our mind a little bit about our labs from lab week to help us with the first part of this question. And then we're going to think about how do we find the pH at the equivalence point for a weak acid, HNO2, strong base titration. And the other thing is, I know that the OH, so we have HNO2, which is my weak acid, and we have our NO2 minus, which is the conjugate base. NaOH is a strong base, so really I'm just talking about OH minus. OH minus is a base, so it likes to take H pluses, so it's going to react with the HNO2 in the buffer. So the NO2 minus is still there from the original, but in this case we know that the OH minus is going to react with the HNO2. All right, so our first step is to figure out the volume, of the sodium hydroxide needed to neutralize the HNO2. So for this reaction, I have my hydroxide, which is a strong base, reacting with my HNO2, which is a weak acid. That we know they're going to react fully to neutralize to make water, and then there's going to be a conjugate left over, or more of it, I should say, produced. So I want to know how much is needed to neutralize so that both of these run out. That's the definition of neutralization. In an earlier section, we found the original amount of moles of HNO2. So we took the volume in liters and times it by the molarity to get us moles. And we know that at the equivalence point, the moles of this acid is going to be equal to the moles of the base because they're a 1-to-1 ratio. So if I have 0.020 moles of HNO2, that means I'm going to need exactly 0.020 moles of OH minus. This is a little messy, sorry, but that's the same thing as the sodium hydroxide. It's a 1-to-1 ratio. So 0.020 moles of OH minus required is the same as 0.020 moles of NaOH. So they didn't ask for moles, though. They asked for milliliters. So I'm going to take the given concentration, 0.1, and then I'm going to take the moles we just found over liters. If I cross multiply, we will get X times 0.1 equals 0.02. So we divide both sides by 0.1, and that gives us 0.20 liters. So I need 200 milliliters. So just multiply this, right, by your 1,000. 200 milliliters. That's my answer to this first part, how many milliliters would be required. Okay, the next thing, if you think of our reaction, BCA, these guys are going to run out, don't care about water. I started with a number of each of these because of the buffer. I had a starting concentration, starting moles, because both of these were present in the buffer. I'm going to make some of this. So I'm going to have a number, an amount of my conjugate base. And because this conjugate base comes from a weak acid, it is going to act like a pretty decent weak base, meaning it's going to influence the pH. This is not going to be a neutral pH because when both of these run out, there's a little bit of this weak base floating around. So at the equivalence point, and this should be familiar of the titrations of a weak acid strong base, think of that video. At the equivalence point, the pH is only determined by this weak base. So I'm going to take this BCA table. Okay, we know that we have equivalence or neutralization, so 0.02, 0.02, both of these run out. I start with a certain number of moles of NO2 minus, which we found earlier because of the 0.25 molar and the 30 mils. So we found that in an earlier problem. Acid base still reacts, so it's a one-way arrow, so I'm making some of this. So I'm starting with some and I'm just making a little bit more. We know that both of these run out, so that means X must be 0.02. So 0.0075 plus 0.02 gives me how many moles of NO2 are present or made or exist at the equivalence point when these run out. And so once the equivalence point is reached, now I just have this mole of conjugate base floating around. So let's divide that by the total volume. This is the weak acid, this is the conjugate base from the buffer, and then this is how much of the sodium hydroxide, 200 mils, we added. So I find a concentration of NO2 minus present at the equivalence. Ignore this for a second, let's move to the next slide. All right, so we have a weak base that is now just sitting there, right? Everything else has reacted. The strong base reacted with the weak acid in the buffer. So there's no more of this to start, no more of this to start. So how do we write a weak base problem? Well, we add it with water. It's an equilibrium. So the water gives an H to this weak base, and then we have hydroxide. So I need a Kb expression, okay? I only have the Ka of HNO2. Well, it's really easy to find the Kb of its conjugate. Ka times Kb equals Kw. So to find Kb, I'm going to take the Kw of water, 1.0 times 10 to the negative 14th, divided by the Ka of the HNO2, and that's how I get the Kb of this conjugate base. So my Kb expression, products divided by the reactant, and I'm going to set it equal to the Kb we just found. Okay, I have a starting concentration. There's none of these to begin. We use it up, or we use some of it. We make some, and so I can fill out my E line, 0.0833 minus x, and x. So now I'm able to just use the Kb, plug in my equilibrium line, solve for x. I did a little 5% rule to make my math easier. When we get x, look at what's here, x and x. X is going to be the concentration of hydroxide. So I have a little bit of weak base. Okay, I have a little bit of weak acid. I have a strong base hydroxide right here. That's going to determine the pH, but it has to be the equilibrium value. So X is the OH at equilibrium. So I can take the negative log of that OH at equilibrium to get my POH, and then we know 14 minus the POH will give me pH, which is 8.16. All right. What is the pH of the solution if you add 10 mils of NaOH past the equivalence point? So now I know we kind of talked titration last time, but now my brain is really thinking of a titration. So I started in this region somewhere because we started with a buffer, a weak acid and a little bit of its conjugate. So imagine I handed you a solution here, and I can actually tell you if this is the halfway to the equivalence point. We actually started a little past. How do I know? Because we have more of the conjugate base than we did of the weak acid, and we know at the halfway to the equivalence point those are equal, like 0.2 and 0.2. But the reality is I had 0.25 of the conjugate, so I was somewhere here in the buffer region. In the last problem, we figured out how much NaOH is needed to get to the equivalence point. Okay, so we figured out, I guess we could say that we found the pH at letter A here. And then for letter C, we found the pH at the equivalence point. We figured out exactly how much sodium hydroxide, the volume to add, and we found the pH. Well, now I want to know, we're going to add 10 more milliliters of the hydroxide. So we are going to be somewhere up in here, 10 more milliliters. So we are after the equivalence point for letter D. So let's figure out how to do that. All right, so for this guy, I know the moles of HNO2 found in part B. I think that says A, but it should be B. And I also know the moles of the NO2 minus found in part B. So I added those to my BCA table. But we're adding 200 mils to get to the equivalence point, but we want 10 mils extra of the sodium hydroxide. So really I'm adding 210 milliliters of NaOH. So using the given molarity and the 210 milliliters, 0.21 liters, let's find how many moles. So I get 0.021. So that's how much of the hydroxide I'm adding, okay? And we know those are going to react a one-way arrow. So to find X, I'm going to take 0.02 divided by 1, 0.021 divided by 1, and clearly the 0.02 is smaller, so that's my X. So I'm going to subtract, add, and this guy gets that original just because we started with an amount of the NO2 minus. So then I see that I have a little bit of excess OH and comparatively a lot of bit of this conjugate base. Don't really care about the water. So the reality is, though, if we have a strong base and a weak base in a mixture, even though I have more of this weak base, anytime you have a mixture of a strong base and a weak base, the pH is going to be determined by that tiny bit of the strong base. Okay, so I only care about the strong base. That's the same for acids. If we have a mixture of acids, the strongest acid is the one that determines the pH. Sure, I could argue that this is a little bit a part of it, but the reality is this is in an equilibrium, so it's even smaller than the concentration we would get of hydroxide, and sig fig-wise, it's not going to make a difference when we calculate the pH. So we're choosing to ignore any hydroxide that would be produced from this equilibrium. Anyways, even though this is really small, I'm going to take that and divide it by the total volume. So that's the weak acid, that's the conjugate base that we started with in the buffer, and we added 0.210 liters. And so I get my concentration of hydroxide after this reaction happened. So it's the excess. Okay, we're going to take the negative log of that to get POH, and 14 minus the POH gives me the pH. So I hope you find this video helpful. That was the question I got the most questions on last year by students. So hopefully that helps you. I know it was really long. Again, I would give you in an FRQ some maybe other acid-based questions and just one of those because they are so time-consuming. But they definitely got you thinking about when we use stoich versus an ice table. It kind of was a nice range of finding the pH of a buffer. There was a little titration there, equivalence point, pH after the equivalence point. So that was a good problem, but it definitely was a little time consuming. But I hope this video was helpful, and I will see you guys later.